I will get to modifying this thing soon, but before I show you my very extreme modification, I thought I would show you a quick modification which makes it slightly better, basically for free. So I have it running here. I didn't bother to put the screws back in. Now you can see this is on 47.1, whereas we had 46.4 before, so we're already slightly better. And if I insert the load, so I knock the probes out then, we're on 6.18. So 6.18 divided by 2 kilo ohms is 3.1 milliamps, thereabout, which is still not in spec, but it's slightly better than what we had before. If you look on this board, you'll notice they used a 3-pin connector for this. Well, there's a trace going to the middle, this end one is the ground. Top one, that goes down to the switch, that comes up. The other side is the 12 volt from the jack, which goes on this trace straight down there. I'll try and keep this brief for the unelectronically inclined. We have the 3-pin connector here. This red one is the signal, this end one is the ground. So the ground just connects to this area. This whole thing is ground, so for XLR1 you can see there's these 4 little things going in, and that goes to the pin. The end one is coming through this top trace, going through a 100 ohm resistor, so that's 101, which is 10 times 10 to the power 1. That gets decoupled with this capacitor, that's an electrolytic on the other side, and that goes through here to these 2 resistors, which are, so this point should be 48 volts, and these are the feed resistors which go to XLR2 and 3. So these pins connect down to here, and these go through small resistors, I can't remember the value. They get decoupled, and that just smooths out the voltage. And that goes back through this 10 ohm resistor and to the middle pin. Now these 2 resistors are loading down the circuit, so by moving these off we have reduced the load. Hold on just a minute there, I screwed something up. So I said those 2 little resistors were for measurement. It looked like that at the time. It's clear to me now that is not true at all. Now there's 3 standards in the Phantom system, 48, 24 and 12, and they each have a different feed resistor. So the 48 should be 6K8, the 12 should be 680. Now if you want to make a box which switches between them, it also needs to switch between these resistors. So what we actually have is something like this. So we have 48 volts, 12 volts, and the 2 switches in effect linked together. So that's going to go open when we switch modes. It's not quite like that, but you get the idea. And we have the 2 sets of resistors, and they're just common together. So this one is going to go open, and that shouldn't affect things. In practice, this doesn't quite go open, and I believe that is actually loading the Phantom supply, which is why my removing them made a difference. But that wasn't for measurement, it was just to get the correct resistor value in. Well, now we've got that out of the way, let's carry on with the video. Now the reason I put these copper bars here, this one was at the top so it's easy to get to, this one is more difficult. These capacitors are a DC blocking feature, so how this is meant to work is there's a trace on the top side which goes from this pin over to this leg of the capacitor, goes through the capacitor, and then it goes out, and this side should just have the AC and not the phantom power. Now there's a similar arrangement of this guy which goes down to the bottom, through the capacitor, and over to here. Now these 2 resistors just define the DC level on this side. They were 100k, I don't know why they didn't use 1 meg, but these 2 will load down the power if you just short these out. It's optional to do this, but I wanted Phantom on this jack as well as this one. I'll show you this from the other angles, you might just about be able to make out the traces on the top side. I've made all the changes to this box that I need to make, so without further ado, let's see if it made a difference. I've put the multimeter probes in, and you can see we have essentially 0 volts. That's just the capacitors charging up from random static and things in the air. Now I'm going to put this DC jack in, and let's see what happens. So we're up to 48.1 volts, and you'll notice that the light did not turn on. If you turn the selector switch, you can see the light briefly pulses on and then turns off. That might give you a clue as to what I did, and nothing happens on the voltage. Now I've got my 2 kilo ohm load. Let me plug that in and let's see what we get. It's a pretty stable 10.75. 10.75 divided by 2000. That gives us the current in amps times by 1000 gives us the current in milliamps. So 5.4 milliamps, which is well within spec. I'll show you the changes I made inside the box, but first let me show you this plug I got. So this is a 48 volt 30 watt plug, which will do us more than 600 milliamps output. It's a universal plug. It's going from 100 to 240 volts. Center positive, and it has one of those country swappable ends on. I bought this second hand on eBay, and conveniently someone has pat tested this already. Thank you, D. Dix. This is the original supply, which will do 12 volts at 150 milliamps. Also center positive, and also a universal supply. And also with a country swappable end. You can see the PCB here. These are 2 unbuffered hex inverters, and they just use a series of surface mount diodes and capacitors, so these SMD capacitors on the back, and big electrolytics on the front. They use those to step up the voltage. There's an indicator LED there, which has this resistor, and this thing you see here is just a block of foam. This is a protection diode or an idiot diode. So if you plug a jack in which is center negative instead of center positive, it won't do any damage. These 2 are decoupling capacitors, and what I chose to do is make the break in this point here. I don't know what's causing these vertical lines to appear, and that just means that this electrolytic cap is protected because it's only a low voltage capacitor. So the first step is to desolder this pin, and I just manually moved the film capacitor so it came out, and there you can see it's fully removed. Now it left a small burnt area. You can clean this up with a small Q-tip with isopropyl alcohol, and that just leaves a nice finish. Now I did use some solder wick to remove the excess solder that was stuck in the hole. Now I needed to break the track, so I used this Dremel in a drill press holder. I really don't recommend these. I would much rather have a small drill press with a 6mm chuck. But you can see here that I just made a hole in this track. I used a small drill bit, which was I think 1.5mm, and that just separates the 12 volt rail going into the chips from the DC jack. I left the diode in circuit, it really doesn't matter. I then used this through hole to install a bodge wire going all the way down to this switch. I could have actually soldered to this pin on the end, but I decided to solder down here. Now, you might notice there are these kind of ugly kinks in the wire. The reason for that is that I use these very nice wire strippers. You can see the part number there. The problem is they have a sort of anvil thing which comes down and crushes the wire against the jaw, and then this part pulls the plastic off, and that leaves this small kink, but otherwise they are really excellent wire strippers. Thank you all very much for watching. I'm especially pleased with the modifications to this guy and how it turned out. We can be confident in our future experiments that the phantom power is as it should be, and that's not limiting the performance of our devices. In the past, I was not able to guarantee that for my measurements of the Fathead Phantom. Now we can be confident that the gain we measure is accurate. I want to thank you all very much for watching. I really appreciate any likes and comments, and I'll see you next time.